Hello and thanks for joining us. Today we are in northern Oklahoma, just outside of Ponca City. And one of the reasons we're here is the building behind me. Probably recognize that as a power plant. And if you're like me, you probably take electricity for granted. I mean, I just expect it to be there when I need it. And that's the other part of our show. Recently, I learned about an organization called the OMPA, the Oklahoma Municipal Power Authority. And if you don't know what that is, well, you're probably not alone. But the more I learned about what it is, the more interesting it got. So if you stick with us for the next 30 minutes, we're going to get inside this place, find out a little bit more about how it works, and we're also going to learn about some of the people and meet some of the people with the OMPA. So if you're ready, I'm ready. Why don't we head inside? Why don't you introduce yourself?
I'm Drake Rice, Director of Member Service for the Oklahoma Municipal Power Authority.
Drake, thank you for having us out here. And where are we located right now?
Right now we're in the control room of the Charles D. Lamb Energy Center, which is about 7 miles north of Ponca City, Oklahoma in Kay County.
And when I was outside, you call it the Energy Center. Is that a big word for power plant?
It is a power plant.
Okay.
It has a 103 megawatt gas turbine that's operated to provide power. It is connected to the statewide 345 grid, 3,445 volts.
Okay.
Messed that up, sorry.
That's okay.
But,
I was going to ask you when you say 345.
Yeah.
I don't know that term.
Yeah.
So that explains it. Okay.
Right.
And gas powered, you say? Natural gas?
Yes, it's powered by natural gas. There's a natural gas power line on one side of the property. The transmission is on the other side.
And you mentioned the Oklahoma Municipal Power Authority. It's right there on your shirt.
We're a group of 42 cities. We only serve cities in Oklahoma that own and operate their distribution systems.
When you say distribution system, what is that?
That's the wires like behind your house in the alley.
Okay. The hardware?
Yeah, it comes to your house. That's what the distribution system is. We're in the generation, plants like this, and the transmission, the big tall towers and things that get the power to those different locations.
And not every city in Oklahoma is part of OMPA?
No, there are 63 municipal systems in Oklahoma. OMPA serves 42.
Okay. And who serves the other?
They're served by Western Farmers Electric Cooperative, Grand River Dam Authority, Public Service Company of Oklahoma, AEP, and OG&E.
Okay, a lot of us are familiar with OG&E.
Right.
Okay. And what are some of the communities that are served, some of the bigger cities?
Okay, Edmond, Oklahoma, Ponca City, of course, Duncan, Oklahoma, Altus, Oklahoma, Blackwell, Perry.
Now, I noticed behind me some good-looking screens. We have a gentleman. Let's head over here.
This is Jim Hendricks, our plant manager here in Ponca City. He's over all of our facilities.
Jim?
Nice to meet you.
Nice to meet you. Well, can you tell me what we're looking at here?
Well, this is the control overview screen for the gas turbine, showing the speed, the amount of generation that we're producing, and then megabars. And of course, all of this data.
Wow.
This is all the different things that the operators are looking at on a continuous basis. And anytime that the unit is up and running, we do monitor voltage and other things when the unit is not called on to produce generation for the system. This is showing the turbine speed, which is 3,600 RPMs, which is typically the standard speed for most turbines and generators because of the amount of poles to the generator and also to maintain the 60 cycles on the system.
Your office, when I met you, is in Edmond.
That is correct.
That's where your headquarters is?
Headquarters is in Edmond, Oklahoma.
And all of this can be monitored from there as well?
Yes, we monitor from there. Actually, they do the scheduling. They get with the Southwest Power Pool, which we're all interconnected with, all the utilities in this region, and they'll tell us what units they want us to run today. And it's based on pricing because it is a market-type program now.
So I just assumed all these power plants are running all the time.
No, they're based on price, and they look at transmission congestion, issues like that, and they schedule the plants, and then each utility runs the plants they're told to run.
So it's not just demand for power like summer when it's hot. There's also a financial aspect to
That's
that.
correct.
I never thought of that.
Right, and that's the whole process is they look to run the cheapest units first, and as it gets more congestion, need more power, they run the more expensive units.
So all this is going on when I flick my
When
switch,
you
and I have
flip your
no
switch-
idea.
Well, and here's the wonderful thing about it. This was all figured out yesterday. They do the scheduling and pre-scheduling the day before, and they even look at day-ahead
So
markets.
it's forecasting.
Yes, they're doing forecasting all the time.
Well, can we go outside and look at the power plant a little closer?
I think we can. Let's get some hard hats.
Oh, okay. Well, here we are outside looking at the power plant. You can probably hear it. Jim, now you say you've been here since this plant was built,
Yes.
and how long ago was that?
It was commissioned right at 2 years ago is when we finished and commissioned the unit for retail.
And you were here when they assembled it.
That's correct.
Can you give me a tour of what I'm looking at here?
Okay, what you're looking at first,
What's this big
is-
tall tower here?
this is the exhaust stack. This is the last point where all of the emissions and everything else from the burn to natural gas, this is the last part of it.
Okay.
And we do have to monitor that on a continuous basis. We have equipment located on the other side of this stack here.
Now, the naked eye, I don't see anything coming out of there.
Well, you're not supposed
Not
to.
supposed
We have to monitor that. We have permitting and everything else that goes along with monitoring that. And then
And what do we go into this?
as we go in here, this is the transition piece. This is actually the exhaust of the gas turbine itself.
Okay.
And
What are these two squares on top of the big square?
Well, there's two squares here, but there's also two to the north over here, and they're all four the same. It's just the design of the inlet vanes.
Okay.
And those are cooling fans for the turbine enclosure.
So this, where it says Siemens, that's where the actual turbine is spinning.
That is correct. And it's turning at 3,600 RPMs continuously. And then as we go to the north, a little bit farther, then you've got the inlet ducts and
Little layered things.
all of this. The layers over on this east side, those are the inlet to the generator.
And they're sucking in oxygen.
They're sucking in air. Now these others here are for the generator to help keep the generator cool. The bigger one up on the top is the actual inlet to the turbine itself, providing combustion air for the turbine.
I don't know if this is a stupid question. What's making it spin? So natural gas
It's the thermal dynamics.
is
of
boiling water?
No, it's
No,
the
okay.
combustion of the natural gas.
It's the combustion of the natural gas.
As the fuel is burned, then
Okay.
it expands, and as it expands, it creates a force that drives the turbine.
Okay. I never thought about that.
Yeah, and most people don't.
Yeah.
But that's how that part of it works.
Okay.
It's as the heat expands,
Yeah.
then that's the driving force for the turbine. Yes.
There you go. I learned something. Kind of understand it, but I learned a little bit. And then what do we have past the intake?
Then on the other side of the intake, we've got a smaller building over there that houses some controls for the starting of the generator's dual purpose. The generator is used to produce electricity connected to the gas turbine, and so it produces electricity, goes back out to the system. But it also acts as a starting motor for the startup of the gas turbine.
Let's head down towards the north end. I see a lot of things that I think a lot of us do see. These large gray poles. Looks like, I call them transformers, but we don't know what they are. They're just stay away from them because they might kill you.
They're dangerous. We don't want you messing around.
Why don't you kind of give us your perspective? What are these things we're looking at?
That's what holds all of the transmission and distribution lines up, keeps it off the ground, and that's basically all of that. What you're seeing back here is we're getting closer to our substation, which is a distribution point where we are connected to the grid through that substation.
Now, do you have to reach a certain level of volts maybe before you can engage the system? Like they're expecting, I don't know, a certain amperage or voltage?
There's a common term called syncing. We synchronize with the system.
Yeah.
So our generator has to be spinning at 3,600 RPMs so that we can get to that. We have a two-pole generator. And at 30,
I don't want to get too technical.
And I'm not going to get too technical. But when everybody, if you look at a piece of equipment in your house, your hair dryer, the toaster. If you read the little label on it, it says 60 hertz or 60 cycles.
Something we just ignore.
And that's
Don't
what
pay
we are
attention.
trying to maintain.
Okay.
So when you are in the summertime and your air conditioner kicks on and it dims the lights just momentarily, well, what it's doing is it's dropping from that 60 cycles, it drops just below that and makes everything a little bit less. Then you got all of these generators out on the system that they pick back up. They'll pick up a little bit more load and brings that back to 60 cycles, and that's how it maintains it.
What is the optimal temperature, outside temperature, that this thing runs most efficiently at?
About 42 degrees is
Pretty cold, and Oklahoma isn't at that temperature that often.
No.
So
No.
what do you do to compensate for the 100?
What we have on the inlet to this is, as you can see from up here in the front, that is a evaporative cooler.
Like a swamp cooler?
Just like kind of like the old swamp cooler, is we have different levels in there where then we put demineralized and what we call potable water or drinking water. We mix those at a certain ratio, and we do that because of the corrosive abilities of water.
Like my shower head gets clogged, you don't want that happening.
Absolutely, and so we do have to clean some of that up every once in a while, and
that brings the air temperature down.
That brings the air temperature down. It's still, and on some units, they have this type of operation. Others have chillers that can actually cool the temperature down. It depends on the amount of money that you want to invest in it, and the amount of maintenance that's required also.
As far as scale, is this a smaller power plant, a medium size for Oklahoma?
This is actually a smaller one, being about 100 megawatts. Now, we do have a couple of other units that are smaller. They're
Physically smaller, or the power generation?
Both. They're both smaller in size and in their capacity.
Okay, Drake, why don't you tell us where we are?
Okay, we're at the Kaw Lake in Kay County, Oklahoma.
Kaw Lake, K-A-W?
K-A-W, named for the Kaw Indian tribe.
Okay.
And this dam was authorized by the Flood Control Act in 1962. Construction began in 1968, was completed in 76. It was built for flood control and to regulate the water for the Kerr-McClellan waterway. The barges come up the Port Catoosa over by Tulsa.
So we're looking at
This is the Arkansas River.
This is the Arkansas River. Okay.
It flows by through Tulsa, Oklahoma, down by Fort Smith, and through Arkansas to the Mississippi.
And where does it start? Where's the head?
Starts up in Colorado, near Salina, Colorado. It's a little stream, comes through Kansas, goes around Great Bend. You've heard of Great Bend, maybe, and by Wichita, and comes down.
Is this the first dam?
This is the first dam in Oklahoma, and actually, I think it's the first dam in the Arkansas.
Yeah.
They may have some regulating dams upstream.
So it was built like this in the 60s.
Right.
And was the power plant here?
No, the power plant was not here. The Corps manager of the project had discretionary funding. He built the substructure.
Which is like the foundation?
Yeah,
kind of?
foundation for the power plant. But it was never built. They never got funding to complete it. A lot of the dams, they have power plants like Keystone over by Tulsa and Robert S. Kerr down by Potomac.
And I know a lot of them will dam up for water reservoir.
Right.
But I always just assumed the hydro plant was always part of the plan, and they always just do the two together. But
no.
And is this used for drinking water?
Yes. The water from this reservoir is used by the city of Stillwater. They take water, and there's other cities looking at. One thing you got to remember, down south of here, the Salt Fork of the Arkansas flows in, and that's why they can't use the water at Keystone. It's too salty. The salinity is too high to clean.
So this is a threefer.
Yes.
Flood, drinking water and power. And now tell me about the power. So it didn't have a plant.
Right.
And when did that start?
Okay, we bought the rights from
OMPA?
OMPA did. When I say OMPA, Joint Action Agency or Joint Action. We bought...
Oh, I'm sorry.
Let's
a
start
Joint
over.
Action Agency, what is that?
Okay, a Joint Action Agency is what we call ourselves. Okay. We were one of the last to be formed in the United States. It's where cities and towns came together to form a generating and transmission power company.
Is Joint Action Committee, is that nomenclature reserved for power agencies?
Well, they have them that do water and different things. But in municipalities gathering together. Okay. In our case, it was done for the electric, and there's about 56 others in the United States. We were one of the last to get formed, by the way. So
that agency...
We bought the substructure from the Corps We leased the ground around it. We have
Okay.
a lease with the Corps. And then we designed and built and installed the hydro generator that uses water off the lake. And we
Did you have to core a big hole in this dam?
No, the like I said, the discretionary funding the manager of the
Yeah.
project had. He put the tube through the dam. It's a 22-foot tube that comes through the
So
dam.
he knew someone's going to use this someday.
They had hoped to put hydro
Okay.
in, and they didn't get funding.
Huh. And so you guys get it, and you've got a platform, you've got a hole. Where do you go from there?
Get a bunch of engineers and attorneys together, and they design
Wow.
and build a turbine that will fit in the hole and use the water from the upside of the lake.
This is the hole I've got. Find a turbine. This is in
Right.
the 80s?
Yes, this was done we began in 1987, completed the project in 89. So, and it's an interesting thing in the process of building this plant. Turbines were not being made in the United States, so the turbine is actually built in Argentina. And there were several places we wanted to keep it in the Western Hemisphere.
Okay.
And so it was brought up here and installed. They lifted it and dropped it in the hole from up on top of the dam with a crane.
So when you need water to generate, what's that relationship? Who
Okay.
is that with?
That is with the United States Army Corps of Engineers.
So they're still running.
They
that
run the
portion.
lake, they handle the water, and they tell us how much water will be discharged. And in our agreement with them, they will discharge it, let us discharge it for them.
Okay.
Because
Sometimes they need to empty it.
yes,
And if you do your part, they don't have to open a gate.
that's correct.
Sure. So you're not wasting water.
Right,
Okay.
and making good use of the water because it's generating electricity, and we pay them for that water. So,
Nice.
Mhm.
Okay. What, can we go inside?
yes, let's go inside. I think Jim's going to be in there
Oh, great.
and talk to us.
Well, here we are. We're back with Jim, the plant manager. Jim, those cranes are very impressive. What are you using those for?
Well, we, on an annual basis, we do outages on these units. We disassemble them and we check parts, check clearances, check for wear on bearings and those kind of things. And so those large cranes are used to be able to lift those pieces of the turbine and the generator, other equipment, and put them in different positions so that we can do those inspections and do the required maintenance.
And you guys can't see them yet, but let's walk that way and show them what Jim is talking about. This is kind of the, what do you guys call this thing we're walking on?
Lay down floor, and as you see the rings and stuff, they pull the things out, and they've got different pieces go in these certain areas.
And you say you take this thing apart about once a year?
Yes, we just finished one in February where all of this stuff was all lifted off, stacked over here on the floor, and then there were readings taken and determining if there's any wear, then what components have to be taken apart. But a large part of what you're seeing here, of course, this is the generator part underneath that, but then down below that, a couple of levels down below is the turbine itself.
And can we get down and see some of the mechanics of this?
Yeah.
Why don't we head that way?
Okay.
So Jim, we're looking at the top of the turbine, is that right?
Well, this is the governor controls for the turbine itself, which will help determine the control the speed of the turbine itself. And you've got the hydraulics, oil lines and things that are going up to that.
And these gauges here, what are these telling us?
These gauges, it's just like any moving piece of equipment, like the engine on your car. We have to monitor bearing temperatures, oil temperatures, and that's what all of these gauges are. What you're looking at here is the butterfly valve, which is basically the inlet shut-off.
So we're looking at the inlet tube right there.
Yes, it's called a penstock.
Okay.
Penstock is the inlet to the turbine itself. This butterfly valve, which you can see this arm here,
Wow, look at that hydraulic.
and the hydraulic cylinder down below,
Wow.
and that's either full open or full closed. In the event that something causes a failure and it goes into a mechanical shutdown, this hydraulics will dump and that butterfly valve goes closed, isolating the water to the turbine itself.
So Jim, what's lower than this spinning structure?
What you're seeing down here, what he's getting a picture of, is actually the rotation of the shaft of the turbine. On each side, there's a hydraulic cylinder on each side that adjusts the wicket gates. And the wicket gates are what will adjust the water flow into the turbine.
Okay. And is the water flowing above us or below us right now?
Below us.
Below us. Is the electrical generator right above us?
Yes,
Okay. So it goes water flow, generator, governor.
that's correct.
Okay. And how deep do we go from this point?
We can go down about another 20 feet.
So Jim, we're looking at the very top of the shaft of the turbine, right?
That's correct.
And I'm trying to figure out in my limited knowledge what controls the speed. I mean, like, does water fall at a certain speed and it turns the shaft at a certain, or do you control that? Or is it both?
Well, it's a little bit of both. We have it's a hydraulic governor control system. That's the white part up on top. And that is a control mechanism so that we can control the speed. And as we had talked about earlier, down below, I don't know if you got a picture or not of the wicket gates. And the wicket gates will also help in determining the amount of water flow through the turbine.
But I imagine there's kind of a, for lack of a better word, a default setting. If you just let water fall out of this dam, it's going to spin it at a certain rate.
That's correct.
And is that too fast? Is it too slow?
Well, the head level on the lake can be a contributing factor on that.
Okay.
And as it changes, as the water level comes down, there's less force. Okay. Being the inlet is as deep as it is, and of course the lake level is determined by the Corps of Engineers.
Sure, lots of factors.
And they are the ones that allow us to release that water and convert that into
So you need a
electrical
governor
energy.
to keep it constant.
That's
There's all
correct.
these other variables.
That's right, because if we didn't do that, as I had stated earlier in an interview, was the fact that we are looking at everything as 60 cycles. So to maintain that 60 cycles, we have to keep it at a certain speed. And as I had stated earlier, with a 3,600 RPM machine,
That's the gas.
that's the gas turbine. That's correct.
Spinning at 36. What is this RPM?
This one is at 132.5 RPM.
132 versus 3,600. That's pretty dramatic.
That is pretty dramatic. But the poles on the generator are the determining factor on that. To be able to get the 60 cycles on this is then you have to increase the number of poles on the generator to accommodate for the speed that you can maintain.
So Jim has passed me off to who? What is your name?
My name is Calvin Beeston. I'm the plant supervisor here at the hydro plant.
Hi, Calvin. Thank you so much. And Jim said you could give us a tour of the dam or the turbine using this diagram. Could you do that for us?
Okay.
So where does the water come in and where does it leave on this diagram?
The water comes in right here. This would be representative as the penstock, the water supply to the turbine. The water comes in here, goes through the wicket gates in this diagram, and hits the turbine blades, which propel the unit to rotate. The idea as the gates are in a annular position. This is a side view of the unit, and there's 24 gates, and as each gate opens up, it controls water flow. As we control water flow, we can then control the speed of the unit.
Is there water surrounding? Or is
Yes.
Okay, so it doesn't come in at one spot. It can come through gates 360.
That is correct.
Okay, I didn't understand that. Okay. And then it flows down out into the
Flows down and goes to the river.
And this is where you're generating power.
This is the generator up here. This is where we generate power. So as the turbine blades and the gates open up, we produce power here in the green area, and the power is then sent to the high electric yard, and then from there to the homes.
And how long have you been working at this plant?
10 years. Yes.
So you've seen this turbine taken apart a number of times.
Yes, I have. Yeah.
Is it really fascinating to see all of that inner working?
Oh, it's very interesting. We do this once a year. We take the unit apart and we do annual maintenance on different components.
Well, thank you very much for the time.
Thank you very much.
So Drake, let's talk about some of the diversity when it comes to your power generating capability.
We have natural gas.
And that's the plant we saw earlier.
That's right. It's a natural gas plant, high efficiency gas. And then we have lignite, which
What
is
is
a
that?
dirt type coal down in Louisiana and Texas. But then we have methane gas, which is over by Sand Springs. There's the only methane plant in Oklahoma.
I think of that methane coming out of a landfill.
That's right. Comes off a landfill.
You're
over
generating power from
That's correct. And they're generating power. We buy it. Then we also have wind, which you see a lot of wind turbines. We have over 100 megawatts of wind power in 2 different fields, one out by Woodward, one over by El Reno.
And that protects you in a number of ways.
Well, right. We're not dependent on one source of fuel. We got the hydro, and we got coal and gas. Now, used to we were heavily loaded in coal, but now we've moved away more to natural gas. We use a lot of Oklahoma natural gas.
Is that your predominant?
Right now, yes, it is.
Percentage-wise?
About 49% of our power comes off natural gas.
Well, you have taught me so much about not only power generation, but also the OMPA. And I think a lot of us have never heard of it, but now we know it's there, and we're glad it's there. Jim, join us here. I want to thank you for the tour of the 2 plants. Appreciate your work.
Thank you for this opportunity.
And thank you, Drake, for all your time.
Appreciate it. We appreciate what you're doing for the state of Oklahoma.
You bet. Well, what can I say? This has been a fascinating day, getting to meet some great people, some great fellow Oklahomans, and all these things come together. They contribute to making Oklahoma grand. Oklahoma Grand is a proud partner with TEAM, an interfaith nonprofit organization determined to break cycles of incarceration in Oklahoma. Visit team.org. Oklahoma Baptist University, offering a fully online MBA in Project and Energy Management, International Business and Leadership. Visit okbu.edu/graduate.
And Producers Playhouse. Creative visual communications for Oklahoma since 1997.
For more in-depth interviews and additional footage from today's show, visit our Facebook page or oklahomagrand.tv.